I'm covering for Lizzie Cross today, who's been a little bit ill, and so perhaps not my specialist area. So as many questions from the audience as possible will help me out in asking some challenging and interesting questions. I'm sure there'll be lots of them. So Ricardo is currently at KTH in Sweden, having done his bachelor's in mechanical engineering at Polytechnic University of Valencia in Spain, followed by both his master's and his PhD at Illinois Institute of Technology in the US. He's worked briefly in industry at Altair Airbus, so some good industry experience there to build on. And since then been at KTH, lots of fascinating papers and interesting stuff. So looking forward to the talk, and thank you very much, Ricardo.
Okay, thank you very much for the nice introduction and for the kind invitation to present in this webinar series. I'm going to talk to you about modeling and controlling turbulent flows through deep learning, and the funding for this project comes from an ERC grant. So we want to start by motivating some of this work. As you can see in this slide by Airbus, you can actually look at the different components of the drag in a typical airliner, and around 50% of the drag comes from friction. So looking at turbulent boundary layers is a good idea if you want to understand some of the phenomena associated with drag. And around 40% of the total drag comes from the lift-induced component. The lift-induced component arises from finite wings due to the pressure difference between the pressure on section side, where wingtip vortices are formed with a quite important effect on the capacity of the wing to extract lift from the flow. So looking at turbulent boundary layers around wings helps us to understand around 90% of the total drag in aircraft. So this is the motivation that we use to build quite high fidelity, quite accurate numerical simulations. For these simulations, we use for many of them, the spectral element code NEC 5000, developed by Fisher and others. This method combines the geometrical flexibility of finite elements with the high order convergence of spectral methods in such a way that we can perform this type of simulations that you can see here. This is a DNS, a direct numerical simulation of the turbulent flow around a wing section at a Reynolds number of 400,000. So it's a turbulent flow. It's actually quite interesting turbulence conditions. And as you can see, we can actually simulate a significantly complex geometry with very high accuracy, and again, the possibility of doing spectral methods. Now, if we want to talk a bit more about these simulations, you see that we perform a number of Reynolds number cases. So we can look at turbulent wings starting from a Reynolds number of 100,000 all the way up to 1 million. And 1 million is a very interesting flow case, because here you start to have aerodynamic quantities of the model which are relevant to a full-scale application, and you can really see the important scale disparity that exists in this visualization at a Reynolds number of 1 million. This database can be found in this reference that you can see at the bottom, Vinuesa and others, International Journal of Heat and Fluid Flow, 2018. And this motivates how we can actually use high-fidelity data to build quite robust data-driven models. That's going to be the second part of my presentation, and how we can try to understand and model quite complex flow phenomena. So you can see that the simulations are quite large. The simulation at a Reynolds number of 1 million involves over 2 billion grid points. So it's a quite large simulation. But of course, conformal meshing presents some limitations. I mean, there's very high aspect ratio elements in the far field limit the capabilities in terms of Reynolds number that can be achieved due to very high pressure iteration counts. And therefore, it's convenient to go in the direction of developing more sophisticated meshing strategies with basically non-conformal meshing and adaptive mesh refinement strategies. This work it was presented by Siavas Tosi in the ELIAS conference, and here you can actually see how we can simulate a wing with a finite dimension where we have actually a rounded wingtip. You can see how this adaptive meshing allows us to track the evolution of the wingtip vortex. We can actually refine in the regions where we need more refinement. We coarsen as we go towards the far field, and we can actually achieve a quite high fidelity definition of this complex flow field. These simulations involve over 1 billion grid points, and on all these cases, we can provide very complete turbulence statistics of the turbulent boundary layers, but also of the wind tip vortex and its impact on the flow and the wake. And so this is very high fidelity data, which again can help us to understand better not only the physical phenomena, but also the machine learning models that we can build. Along these lines, I want to show a little video of the type of simulations that we can actually do. So this is a high fidelity simulation of the flow around a wing with a rounded wing tip at a Reynolds number of 200,000, so it's a quite high and turbulent Reynolds number, angle of attack of 5 degrees. This simulation requires 1.5 billion grid points, and you can actually see the mesh and also the development of the wind tip vortex. And so here is where we can actually see how the vortex forms from the pressure to the suction side. So it rolls up due to the pressure difference. It spreads downstream, interacting with the turbulent boundary layer on the suction side and having a very important effect on the wake. You can observe the high level of detail that we can obtain in these simulations and how this wind tip vortex is actually inducing a negative velocity. It's basically pushing down the wake, introducing that vertical motion, such that it generates an additional component of the drag, the lift-induced drag, which basically decreases the possibility of generating lift of the wing in that particular configuration. So clearly this is a quite complex system where you have the wind tip vortex coupled with the wake, and you have an effect of partial relaminarization of the turbulent boundary layer. You can actually have a non-trivial coupling between the wind tip vortex and the wake. You can see here in very high level of detail the coherent structures that form around this wing. These are vertical structures, and you can see how the wind tip vortex is really impacting significantly the flow physics in this complex configuration. We're also going to see soon how this has an effect on this relaminarized turbulent boundary layer when we look into the wake. Let's remember that the effect of this wind tip vortex on the wake is what's actually going to produce the effect on the lift-induced drag that we're going to obtain in these wings. So these are very, very high fidelity simulations, again performed by Siavash Toshi, who is a senior researcher in my group. This is in the LES. And all this data is basically what can motivate the development of quite robust data-driven methods. No? So the main topic of today is precisely on how to use the high fidelity data, the complex turbulent flow data that we have available to be able to develop quite effective machine learning models. Okay, so if we look at a bit at a historical evaluation, 20 years ago, Milano and Komosakos started using neural networks to predict the near-world region of a turbulent channel. There has been more recent work on subscale modeling for LES, development of inflow and boundary conditions, possibilities for developing better runs simulations and flow control, and also improvement of the sensing that you can have from measurements through physics-informed neural networks. So there's a variety of applications where machine learning can actually help in the area of fluid mechanics. More concretely, I have a review paper together with Steve Branton, who is incidentally the next speaker of this webinar series. This is published in Nature Computational Science, so you can see the reference here, where we actually assessed how machine learning can help computational fluid dynamics. And we identify 3 main areas where machine learning can actually help. We can accelerate direct numerical simulations, we can improve the modeling, both in the context of runs and LES, and we can develop better and more robust reduced order models. And this reduced order model aspect, I'm going to be talking about it today in quite some length. So machine learning can help CFD. We are not talking about replacing CFD at all. We are just talking about being able to improve certain procedures or certain aspects within the CFD process and the data analysis associated with computational fluid dynamics. Now, having said this, today I'm going to show you several examples in which one can use machine learning to improve various machine learning applications in fluid mechanics. No? So we're going to look at various examples which can be benefited from data-driven methods. In the first example, we're going to talk about non-intrusive sensing. So non-intrusive sensing is basically what we can use to be able to, for example, measure at the wall of a turbulent flow and sense what's happening above the wall. So we're actually not using a sensor to perturb the flow. We're measuring indirectly at the wall, and we're predicting what happens above the wall. And that's a little bit the idea. And that's interesting because it allows to perform closed loop reactive control. So if we can see what the flow is doing, we can develop better strategies to fight the flow and to be able to control it. And basically the quantities at the wall that we will consider are the two wall shear stress components and the wall pressure, and we're going to predict above the wall the three velocity fluctuations. And we will use several computer vision architectures, including convolutional neural networks and also more advanced techniques of deep learning. Now, this is work performed by Luca Guastoni, who is a PhD student in my group, and this is published in the Journal of Fluid Mechanics. So you can see the full reference here for all the details of this work. The first thing that we did was to perform direct numerical simulations. This is a turbulent open channel at friction Reynolds numbers of 180 and 550. And the idea is to use this data to be able to establish a mapping between the wall information and the fluctuations above the wall. Of course, turbulence has a quite pronounced spatial behavior. So you have coherent structures in the flow that can be effectively exploited in space to make predictions. And that's why fully connected networks are not going to be so interesting, because we cannot exploit that spatial information that we have in turbulence. Convolutional neural networks, which are based on the convolution operation that you can see here at the bottom. A convolution operation basically relies on this kernel that you can see here, where this little window is sweeping through the input, and through the application of the convolution, we obtain a feature map. In this case, each point of the output receives information from 9 points of the input, and these convolutional neural networks are allowing us to effectively understand the spatial distributions of the data, and we are actually able to exploit those spatial distributions to make better predictions. So this is a very important tool in the context of computer vision. And I'm going to show you the architecture, or one of the architectures that we consider. In this architecture, we have 3 input planes. As I mentioned, the 2 wall shear stress components and the wall pressure, and we have 3 output planes. Those are the 3 velocity fluctuations above the wall at a particular wall normal location. And in this case, we have 6 hidden layers with the number of filters per layer that I'm indicating in this figure. Now, this is one example. In some of our more recent work, we use much deeper networks which perform even better with the same number of parameters. So if we make narrower layers but deeper networks, maintaining the number of parameters constant, we can actually perform better. But in this example, with 6 hidden layers, we get outstanding results in a number of applications. This also shows the first layers are identifying features which are smaller and which are more abstract in our data. And due to the concatenated application of convolutions, I can build progressively towards more complex features in the flow and larger ones. Those are the interesting properties that we can observe when we do all the concatenated application of convolutions. So convolutional neural networks are learning in a hierarchical way, going from edges, recirculations, basic information in the data, to hierarchically build complex flow features present in the flow. So the hierarchical way in which the network is learning is similar to the hierarchical structure of turbulence from smaller to larger scales. So in a way, we can actually have a quite suitable tool to at least try to learn something from the flow, from the turbulent flow. So this is what happens with CNNs. This is the problem setup. So on the left, I'm showing you the wall information, which is my input. And on the right, I'm showing you the velocity fluctuations above the wall, which are my output. This is shown at alpha of 550, so at the high Reynolds number. And again, all the information is in this JFM reference, and you can see at the bottom. Now, what I showed you so far was what we call the FCN method, fully convolutional network. So I use all the information at the wall to predict all the information above the wall. At the same time, we propose an alternative method, which is what we call the FCM POD, the fully convolutional network combined with proper orthogonal decomposition. Proper orthogonal decomposition is how in fluid mechanics we call PCA, the principal component analysis. It's basically the same algorithm. So what we do is that we divide our domain into these smaller subdomains, and in each of them we apply the POD. That means that the spatiotemporal problem can be divided into spatial modes and temporal coefficients. And our goal with the neural network will be to predict those temporal coefficients because we effectively decouple the spatial and the temporal information. So having introduced the various methods, we can show some results at r eta of 550. This is the stringwise velocity fluctuations. The first column is at y plus 15, so that's close to the wall. The second column is at y plus 100, that's farther away from the wall. And the third row is the DNS, that's the reference, and that's what we want to predict. The first row, this one over here, that's a prediction based on the extended POD. The extended POD is a linear method formally equivalent to linear stochastic estimation. So we establish a linear relationship between the input and the output. And what happens is that turbulence is inherently nonlinear, and the interscale interactions are nonlinear. In particular, we have one part which is linear, that's the superposition, and then big part which is nonlinear is the modulation. So with a linear method, we can only reproduce the linear superposition. That's why you see that the streaks and the structures that we identify, they exhibit quite some attenuation of the fluctuations compared with the reference, and also you see less streaky behavior, less span-wise movement of those streaks, because some of those complex nonlinear dynamics are actually lost because of the linear method. In the last row, we show the FCN method, so where we use the whole input to predict the whole output, and we see that at y plus 15, the agreement is excellent. We can get a very good representation of the flow at y plus 15. And farther away from the wall, the results get a bit worse because the data is less correlated, obviously, but the FCN POD method exhibits very good performance compared with the reference. So, of course, what happens is that close to the wall, doing the POD doesn't give you so much benefit, but farther away from the wall, where the dynamics is focused on fewer large features, then doing the POD to encapsulate into few POD modes most of the large scales actually pays off and allows you to obtain quite reasonable predictions just predicting the temporal coefficients. Now, this is the instantaneous performance, but one can look at the turbulence statistics. So what I'm showing you in black is the DNS, and these are in the left, center, and right panels, we have the stringwise, wall normal, and span-wise velocity fluctuations. The triangle is the FCN method, where I predict the whole signal. The dot is the FCN POD, where I use the POD coefficients. And the square is the extended POD, which is the linear method. Now, clearly, the linear method is worse. It's really not able to consider all the nonlinear interactions in the flow. Close to the wall, the near wall peak is predicted with less than 1% error with the FCN, which is actually excellent. And far away from the wall, the FCN POD becomes the best method, where I have around 26% error. Now, turns out that close to the wall, we prefer to use the FCN, and far away from the wall, we prefer to use the FCN POD, where this 26% error is a quite acceptable level of error for the type of predictions that we are actually trying to conduct here. There is one aspect which I believe is quite interesting, and is that of transfer learning. So transfer learning is a method which relies on using what we learn for one task for another task that is not too similar but not too different from the original. And in this case, we're taking the flow at r eta 180, so that's the low Reynolds number. And what we do is that we take the network trained to predict at y plus 15, and we want to see how it will predict at y plus 50. So far away from the wall. What we do is that we freeze the first 3 layers and we retrain the 3 last layers with the assumption that the 3 first layers are going to be looking at smaller and more abstract features, which are similar, closer and far away from the wall, and the larger scales, which are identified by the last layers, are going to be more different, close and far away from the wall. So doing this, what we get is that the network with transfer learning has the same performance as the original one, but the training time is reduced to 23% of the original. So we can significantly reduce the training time in this new architecture. Now, these results can be found in this journal, in the Journal of Physics conference series, so all the details are here. But another example of transfer learning, which I believe is even more interesting, is from low to high Reynolds number. So what we do is that we take a network trained to predict at arithmetic 180, that's at low Reynolds number, and then to do the same prediction at arithmetic 550, what we do is that we transfer the weights from low to high Reynolds number, and then we continue the training from the transfer weights. Doing so, what we can get is, again, the same level of performance, but we can reduce the amount of training data by a factor of 4. So this is actually quite amazing, because if you think about it, the simulation at 550 is significantly more expensive than the simulation at 180. So if I can do most of my training at a very cheap simulation that I can run in my laptop, then the requirement for a more expensive high-fidelity data at high Reynolds numbers is significantly reduced. So transfer learning, I believe, is an essential tool to consider in fluid mechanics when we're using machine learning, basically for scientific computing. Now, another example that I want to consider is non-intrusive sensing with lower resolution at the wall. So far, I assumed that I have all, if you take the wall plane, I would have all the information at the wall, but in reality, if you have an experiment, you will only have a few sensors, a few measurements. So I want to see what would happen if I don't have all the information from the DNS at the wall in my input. And to do that, I consider another architecture, which is what we call the Generative Adversarial Network, GAN. A schematic of this architecture is shown here. And this architecture has two parts. No? It has one generator and one discriminator. The generator is tasked with producing high-resolution images from low-resolution ones by fulfilling the statistical properties of the reference data. And the discriminator has the job of identifying if a particular image in high resolution is real or it was faked and produced by the generator. Now, these two architectures have antagonic roles. They're trained together using game theory. And at the end of the day, I will obtain a very good generator that is able to produce very realistic images. Using this GAN architecture, I can produce this network that you can see here, where I use low resolution input data from the wall. Then I use the GAN to produce high resolution data at the wall. And using the high resolution data at the wall, I will produce the velocity fluctuations in high resolution above the wall. This is actually quite an interesting approach. By the way, this is work by Alejandro Güemes and collaborators, and this is published in Physics of Fluids. So you can see all the reference, all the data here, all the references here. What I'm showing here is the stringwise wall shear stress. So this is the DNS, this is the reference. In the first row, I'm reducing the resolution by a factor of 4, 8, and 16 squared. So you can see here that in a very, very coarse input, I basically have no information about the coherent structures. And in the second row, I'm showing you the predictions. So the second row is to be compared with this reference over here. What you can actually see is that the data in the prediction looks very realistic. Not only that, in the low downsampling case, the agreement is pretty good with reference, but even in the high downsampling case, I mean, this is a very, very coarse input, the streaks are where they need to be. They have the right length and the right spacing in the span-wise direction. They are just slightly attenuated. So if I want to do flow control, for me, the important thing is to know where the streaks are. And that's something that I can achieve by using this GANS architecture. And so in principle, this is a quite promising approach. If I try to predict farther away from the wall, what I'm showing you in the columns are the different wall normal locations. So this is where plus 15, 30, 50, and 100. So I'm going progressively farther and farther away from the wall. And the rows, the first row is the DNS, that's my reference. As I go down, I increase my downsampling. So I have a downsampling factor of 4, 8, and 16 squared. Now, clearly the easiest prediction to make is this one, when I am close to the wall and downsampling is small, and I can get a very, very good prediction. But the most challenging prediction is going to be this panel over here, the one on the bottom right, which I want to compare with the one on the top right. And even in that case, of course, I see a significant attenuation of the fluctuations. I miss a lot of information, but the large scale streaks, they are still where they need to be with the right sizes and locations. So once again, if I want to do large scale control, I can effectively exploit the capabilities of GANS to do it. So even with a very coarse input, with resolutions comparable with those that you would have in an experiment, I can actually perform this flow control in a very, very effective way. So GANS is a very good tool for this. The third example that I'm going to show you is going to perform the opposite task. So instead of using the wall information to predict farther away from the wall, I'm going to use information from far away from the wall to predict closer to the wall. And the motivation of this comes from wall models. So in principle, if I can replace all the near wall region by a boundary condition, then I will be able to significantly reduce the computational cost. And we use convolutional neural networks for this. All this work is in arXiv. So this is work by Ari, also collaborating with my group. And all the details can be found in this arXiv paper. And these are the results. What I'm showing you here are the stringwise velocity, the velocity fluctuations in the stringwise, that's the first column, wall normal and spanwise directions, in the second and third columns. Here we're trying to redo a little bit what Mizuno and Jimenez did in a turbulent channel. So we're going to take the plane above the wall at the end of the overlap layer and try to what Mizuno and Jimenez did was to rescale closer to the wall, exploiting the self-similarity hypothesis of turbulence in the overlap region. What we're going to try to do is take a plane at y plus 100 and try to use a fully convolutional network to predict a plane at y plus 50 closer to the wall. So we're going to try to establish that mapping over there. The first row is at y plus 100. That's my input. The second row is still the DNS at y plus 50. This is my target. And my output is the third row. So I want to compare the third row with the second one. Now, the U prime, the string of velocity fluctuations, are in very good agreement. The wall normal and spanwise exhibit some discrepancy, but still I can get most of the features right in my predictions. Here, I should say that the prediction from far away to close to the wall is more challenging for two reasons. The first one is that the receptive field is very small, and I'm trying to really extract information from very large scales from a very small receptive field. And also that I'm losing the small scales. I mean, in the wall, you have the effect of the larger scales on those smaller ones, but when I try to do the opposite, my input lacks the information of the smaller scales. If we look at the spectra, that's what I'm showing in the first row, the shaded contours are the reference and the orange lines are the predictions of the pre-multiplied power spectral density in U, V, and W. You can see that the small scales are missing, or some of them are missing, and there is a small effect on the larger scales. What I can see is that the predictions in U are actually quite good. I get 19% error. V and W are still reasonable. But even if I would get perfect predictions of the closer plane, this would not make up for a good wall model. One is to come up with something more creative, something smarter for a wall model. But as a prediction exercise, this is actually a quite interesting assessment, no? Because we can really see where the limitations are, and we can learn two things. The first one is that the problem with the receptive field could be bypassed with max pooling, for example, with a smarter normalization of our data. And the missing scales could perhaps be reconstructed with GANS, no? Using the work published in Physics of Fluids that I mentioned before. So there could be some interesting extensions of this work to try to improve our capabilities in predicting closer to the wall. Okay. Now, the next example is going to revolve around developing reduced order models. This is something that I mentioned in one of the first slides when I talked about the potential of machine learning. Turns out that POD, proper orthogonal decomposition, or PCA, has two interesting properties. No? You obtain a series of modes in your reduced order model which are optimal in a linear sense, and they're orthogonal, which is interesting for interpretability of these modes. However, because this relies on linearity and turbulent flows are nonlinear, we're going to require many modes to obtain a significant reconstruction of the flow. What we want to do here is to use autoencoders, which are deep neural networks which embed the nonlinearity, while retaining the orthogonality property and being able to get a hierarchy of modes which have descending contributions to the reconstruction. And that's what we're going to try to do. And this is work by Hamid Reza Ibasi, also in my group, published in Expert Systems with Applications. So you can see the reference here to see all the computational details. Also, all the codes are available. And we did this exercise in this flow, which is a high-fidelity simulation of a simplified urban environment. You can see two obstacles. You can see the turbulent fluctuations and the vertical structures around these two obstacles. The references are here, Torres and others, and Lazpita and others in physics of fluids. And we use over 1,000 instantaneous snapshots, perform the simulation with NAIC 5000 to train the model and develop this reduced order representation of the flow with autoencoders. Okay. So we first consider convolutional autoencoders. Of course, the convolutional neural networks are interesting because, well, essentially we can get the possibility of exploiting the spatial correlations in the data. And the other thing that is interesting of these autoencoders, this is what it looks like, is that I start with my input data. I progressively downsize my information with a concatenation application of convolutions in such a way that I reduce the dimension of my data to a minimum expression in this latent space. And then I upsample my data again in this second part, which will be the decoder, so that I can recover the original data. So the autoencoder is an architecture that is trained to recover the original data by obtaining basically a very compressed representation of my data in this latent space. And this is what I'm actually after. Of course, the regular autoencoder doesn't have any interesting property of optimality or orthogonality. Hierarchical autoencoders, which were proposed by Fukami and others, are interesting because they can help us to develop a hierarchy of modes. So I have an autoencoder with a dimension size of the latent space of 1. That gives me a first latent variable. Then I go to a second autoencoder with a dimension of 2 in the latent space. If I fix my first latent variable, I'm going to get another one, R2, basically, with less contribution to the reconstruction of the signal. And if I do that recursively, I will end up with a sequence of latent variables which have less and less and less contribution to the reconstruction of the data. This is hierarchical, but still these modes are not orthogonal. If I want to go to orthogonal modes, then I need to resort to the context of variational autoencoders, which allow me to introduce stochasticity in the latent space. Here, P of X is the distribution of the original data, P of R is the distribution of the data in the latent space, and the goal is to maximize this function, which is the marginal likelihood, which is basically the approximation of P of X given the parameters theta of my network. Now, in variational autoencoders, what I have is a probabilistic decoder, which is basically a generative model, taking me from the latent to the original space, and a probabilistic encoder, which is a recognition model, taking me from the original to the latent space. So these are the conditional probabilities that are important, the conditional distributions that are important for my data, basically. And what I can actually do is that I can look at this, well, basically the encoder is following a Gaussian distribution with a mean and a standard deviation. And I can sample from the latent space with normally distributed noise. So that's basically allowing me to define the latent variables like this. And my loss function in the beta variational autoencoder can be defined like this. So basically this term that I have on the right with a hyperparameter beta is allowing me to learn statistically independent variables in the latent space by minimizing the distance of P of R and the product of its marginals, basically. Now, this is interesting because it allows me to do two things. I can learn a latent space representation, which is disentangled, first of all, because of the statistical independence, and parsimonious because this promotes many of these latent variables to be zero. And that's a little bit the context of what I want to do. Now, if I look at my setup, this is what the decoder would look like, taking me from the latent to the original space. This is what my encoder would look like, taking me from the original to the latent space. In the latent space, I have my mean, my standard deviation, and my noise that makes up basically my latent variable in this case. So this is what the flow looks like. These are basically the stringwise velocity fluctuations. This is the reference. Red and green are high and low velocity fluctuations. And I'm going to look at a reconstruction from 5 modes. So on the bottom right corner, I have the reconstruction from 5 POD modes, which basically gives me back 32% of the energy. It's a very low reconstruction. And the 3 autoencoder-based approaches that I described before give me around 90% of the energy being reconstructed. So the non-linearities in the autoencoder allow me to more effectively encapsulate the data and compress in the latent space in a better way. I need fewer modes to reconstruct a higher fraction of the energy. Not only that, if I look at the flow between the 2 obstacles and I zoom in, that's what you can see here, I can find regions of high and low velocity, these concentrated regions, which they are lost by the POD. The POD doesn't really manage to reconstruct these regions, but the 3 autoencoder-based approaches manage to reconstruct these, these coherent regions of a strong velocity fluctuation. And this is very important. If we look at the orthogonality by looking at the determinant of the cross-correlation matrix, obviously the POD has 100% orthogonality. The beta variational autoencoder gives me over 99% orthogonality, which is excellent. And the 2 other autoencoder approaches, the convolutional and the hierarchical autoencoder, they both have 87% orthogonality, which means that I cannot really have so much interpretability of the modes, and I will lose quite some parsimonious capabilities in my latent space. If we look at the effect of beta, which is the penalization factor, what we see is that clearly a higher value of beta, which is shown in the horizontal axis, will give me a lower reconstruction of turbulent kinetic energy. This is this blue line over here. Of course, if my loss function is giving more weight to the orthogonality, the reconstruction will be worse, but we will increase more the orthogonality. So higher values of beta, if we follow this red line, will give me a much higher orthogonality of those modes. Also, if we look at the latent variables that you see on the left, we can see that the higher the value of beta, the more zero variables that I have. So in the largest value of beta, I only have 3 non-zero variables in the latent space, which again gives me a very parsimonious representation of my model. Okay. Now, this is important because with these non-linearities of my autoencoder, I can actually get a very compact reduced order model of the original system. But not only that, I can actually get very good interpretability of those modes. Here I'm showing you the first 5 modes. The second column is the POD. So this is the known POD. And of course, this is a flow that has quite pronounced separation points and shedding, because of the sharp edges that I have in my geometry. Now, the POD modes are able to identify the large-scale shedding quite well. That's a feature of these POD modes. In the third and fourth columns, I'm showing you the convolutional and hierarchical autoencoders, which basically give me a combination of high and low frequency noise. But I cannot really learn much about the physics from these modes over here. If I look at the beta variational autoencoder modes, which is the first column, what is interesting, these are orthogonal, is that they can be interpreted. And actually, the beta variational autoencoder modes are similar to some extent to the autoencoder modes. So I can actually see that the features, the large-scale shedding is very well identified by the variational autoencoder modes, but those modes also include higher frequency content. So to some extent, I have the basic POD features, and then I add some turbulent fluctuations on top of that, so that instead of having 500 modes, I can only require 5, and then get a very good reconstruction of the flow. So that's a little bit the idea, and we can actually sort the modes in terms of the reconstruction contribution to the signal in such a way that I have a hierarchical and orthogonal set of modes in this reduced order model. So I can have a very compact reduced order model with very interesting properties from the interpretability point of view. Okay. And the last example has to do with flow control with deep reinforcement learning. So in deep reinforcement learning, what I have is an agent, which is the neural network, that interacts with an environment. In this case, this is the CFD solver, through actions. And these actions can affect the state of the system, and the system also gives us a reward. And the reward is a measure of the quality of those actions under a certain norm. Now, what we can do with reinforcement learning is to define a policy pi, which gives us the set of actions A, which are optimal given the state of the system, so as to maximize the expectation of the reward in the long term. This is work performed also by Luca Guastoni from my group, and this was presented last year in the EPS. There's several publications coming up on this work. And what we want to show is a first simple example of a 2D channel where we induce a separation bubble. So in the upper wall, I'm actually doing suction and blowing, so I can separate the flow. This is the recirculation bubble. And what I want to do, is actuate upstream of this bubble so that I can reduce the separation length. And this problem has a classical solution with periodic forcing to be able to reduce the separation length. What we want to do is see if the reinforcement learning can come up with a more sophisticated and more nuanced control strategy. And that's, I mean, the setup looks like this. This is my flow. The color region is the negative velocity, so that's the bubble. These orange spots are the probes, which are basically the locations where I'm measuring my flow. And this square here is the place where I apply my actuation. My actuation is modeled by a volume force, which mimics blowing and suction at the wall. And my reward is this arrow, which I want to shorten. I want to make the reward as the reward will be to minimize the length of the separation bar. Okay. Now, the results look like this. If I look at the video that I'm showing you on the left, what I can see is that the reinforcement learning is sending waves, so these wave packets, and these pulses have at least two frequencies, one associated with the separation of these wave packets, and another one associated with the length of the bubble, the characteristic length of the bubble. So compared with periodic forcing, which will be basically forcing at a single frequency, the DRL is actually giving me something more sophisticated, something a bit more nuanced. And that's actually something that we can see in the results. The periodic forcing gives me a reduction of the bubble of the separation length of 20%, whereas the deep reinforcement learning gives me around 30% of the reduction of separation length. So actually, I can outperform the classical method through the more sophisticated control strategy that I obtain with the DRL. So this is interesting. This has a lot of potential to discover new control strategies in turbulent flows. And this is very recent results that we applied in turbulent channel. So in turbulent channel, we applied blowing and suction at the wall. And we compared with opposition control. In opposition control, we're basically trying to oppose the near wall fluctuations in the channel. In the deep reinforcement learning, we just give each point freedom to actuate in the way that it wants. In a minimal channel, where we restrict a bit the dynamics of the flow, we get 40% drag reduction using DRL and 30% using the classical method of opposition control. So once again, now in a 3D case, in a turbulent channel, in a meaningful case, we can actually outperform the classical method for flow control. In a full channel, we can actually extend the same policy from the minimal to the full channel at Reynolds friction Reynolds number of 180. This difference still persists, so I still can outperform the possibilities of drag reduction with opposition control by using the deep reinforcement learning, which once again, I believe can bring a lot of opportunities for flow control in a wide range of configurations. Okay. And this is a summary of what I have discussed today. I have told you about non-intrusive sensing using CNNs and GANS. I have also told you about the possibilities of reconstructing flow fields, using autoencoders for reduced order models, and also using deep reinforcement learning for flow control. This is my contact information, so you can see my email, my web, and also my social media information. So you always feel free to contact me for collaborations, ideas, or comments. I'm always happy to discuss. And for now, I would like to thank you very much for your attention, and I will take your questions.
Cool. Thank you very much, Ricardo. That was an awful lot of different material, and I noticed on the publications, it's all really quite recent as well. So a lot of very interesting research there. I guess from my perspective, I'm really interested in the sort of transfer learning aspects and the different tasks.
Yep.
So I guess to start with, like, how many different tasks have you managed to stretch this transfer learning to at the most?
Yeah, that's a good question. So far, we have only restricted to going either farther away from the wall or a higher Reynolds number. But we are actually working on a continual learning framework to be able to have a wider range of Reynolds numbers where the network would perform well in each of those Reynolds numbers. So this is ongoing work, but there is some interesting directions over there.
Cool. And with that, have you tried sort of conflicting tasks where, like, perhaps like in some regions you get some benefits to taking some sort of, or replicating some behavior, but it might be different in a different task?
No, actually, we haven't tried that yet, although it sounds interesting. Of course, when you are going to higher Reynolds numbers and farther away from the wall, the physics changes significantly, no? So then in the old task, it's not performing so well. That's why the continual learning could be interesting to be able to maintain a balance in all the tasks. But that's certainly something to keep exploring. Yeah, absolutely.
Yeah, I think it's really interesting, just like the task capacity of different neural networks and how far they can be stretched. I think there's some interesting work there.
I agree. Yeah.
Sorry. Oh, sorry, I thought you had a comment. In terms of the deep reinforcement learning research as well, I think another really interesting area of applications. Did you notice during the training process that you got any sort of unsafe behavior as you were sort of training your simulations?
Do you mean if we would deploy this in an experiment or in a?
Yeah.
So everything is numerical. So everything is done in a numerical setting. Of course, we're working on implementing that on an experiment as well. And then, of course, the safety aspect is very, very crucial. We have capped the amount of control that we can use. So we don't have extreme control actuations. We don't have too much blowing or too much suction, at least in the tests that we are doing, because we wanted to have a comparison with a classical method, given the same amount of flow being injected or sucked from the flow. So then there was a quite strong limitation on the amount of actuation that could be done. But then, of course, if one goes into larger, more ambitious control goals, then looking at how much flow is being used and whether you get, for example, if you put this in an airplane and you start to blow very much, then you will lose lift. And then you might have a condition that is not very, very safe and very stable. So then with experimental deployment of all these methodologies, it becomes very relevant, no? All these safety implications that you mentioned. Yeah. And of course, actually, in the 2D cylinder, this is an example that I haven't shown today, but we have been doing things in the 2D cylinder. One restriction that we impose in the reward is to have, we want to reduce the drag, but we want minimal fluctuations of the lift, which is perhaps, you want something that is still consistent from an operation point of view, basically.
And what were the sort of training times on these sorts of reinforcement learners for the control?
These are so far quite small cases and there is a parallelization of the episodes. So you have a bunch of, the channel case is maybe 8 different instances with 8 different episodes that are being trained simultaneously on 8 CPUs. And so it's not a very, very large case. Some of these 2D cylinders at high Reynolds numbers that we're exploring, those ones become more computationally intensive, right? Because you really have many different episodes in parallel. The simulation, the CFD part becomes more expensive. And in that sense, we're looking at more effective strategies for parallelizing this in higher Reynolds number configurations. So deep reinforcement learning is expensive, but I believe there are effective ways to parallelize the effort, at least to some extent.
Yeah, I think we're doing something similar perhaps, and I think our concern is how long it takes in the real world to actually train and whether people will put up with those training times once they're actually on a real application.
It is true, but the idea for us would be to do all the training in a simulation, mimicking the experimental limitations that you have in the real world, basically. So, of course, in the simulation, the data is perfect. In a wind tunnel, you have experimental errors. So you will be able to mimic those experimental errors in your simulation and do all the training in the numerical setup. And then once the model is trained, just deploy the policy, the learn model in the experiment. So then the evaluation of this is very fast. The training is done offline in principle.
Cool. That's really interesting. I think there's a lot of stuff we could probably talk about after this, and I may well send you some papers and have a chat.
Let's do that.
Thank you once. Thanks once again for a really excellent talk. Really enjoyed this one. and we'll make sure it's well advertised on the video so people can watch it in the upcoming months. Thanks once again, Ricardo, and I hope you enjoy your evening.
Thank you very much. I enjoyed very much the conversation and the presentation. I'm happy to keep discussing, and this is very exciting stuff. And yeah, thank you everybody for attending.